Let's launch into Chapter 3. Chapter 3 is all about the shapes of functions and their mins and maxes and derivatives and stuff. Often we want to minimize or maximize something like maximize number of lives saved, minimize cost, maximize profit, minimize risk, minimize time spent. Optimize is a general word for either minimize or maximize. Just make it the optimum, make it the best. Let's do a little bit of advertising. In business or industry or all these other things, they often have millions of variables in one problem. So just one example, consider a large pizza chain in the US. They have 8,000 locations. They might have 100 warehouses nationwide, and they have to decide how much product to send from each warehouse to each location to minimize their total trucking costs and inventory costs and stuff like that. So for each location, they have 100 warehouse variables saying how much should this warehouse send to this location. So that ends up being 800,000 variables. So that's how you can get into the millions of variables quite easily. Here at EMU, we have math120, which I teach, and there we can handle like 5,000 to 10,000 variables, and we're doing that in Excel or Python or R. In math120, we easily handle 200 variables. That's kind of the limit for what Excel will optimize for you for free. But we could use Python or R if we really need to when you take 319. In Calc 3, we often have 2 to 3 variables, and we're doing that by hand. And here in math120, we're starting simple with just one variable, and we're doing that by hand. And we're doing it by hand so we can kind of take the first step on this ladder of, well, how do we program computers to kind of do what we were doing by hand so they can do all the grunt work for us in these larger problems. So it might feel silly to just do it by hand, but we're understanding the basis of these fancier problems. So our main goal is to find the x values that give the minimum or maximum function values. So let's consider a few examples. Let's say you have a bioreactor, so you have some yeast or bacteria in a big solution, and you're trying to get them to make medicine or yogurt or something. And you can control the temperature it runs at by running heaters or coolers, and you want to choose the optimum temperature. What would a graph of that situation look like? What would be your x variable? What would be your y variable? What would the shape of the function look like? So take a second and sketch that out. Pause the video. All right, welcome back from pausing. So usually anything that you can directly control, you're going to put on the x-axis. So if we've got heaters and coolers and stuff, we can control the temperature, and we're hoping to get a good yield. Well, if the temperature is too low, I'm not sure the exact biology here, but you can imagine if the temperature is too low, your yeast or bacteria or whatever aren't going to be able to do very much for you. They'll just kind of be hibernating or whatever the equivalent is. So for low temperatures, you'd have a low yield. Also, if they're too warm, maybe they can't survive, and you'd have a low percent yield. So we put percent yield here. Percent yield is what percent of the total you should get out are you actually getting out. And so somewhere between those two, there might be a curve like that, and we're looking to find that x value that gives us the highest percent yield. In a more kind of industrial or business situation, if you're making products, you could inspect all of them, you could inspect half of them, you could inspect 1% of them before they go out the door, and there's different total costs for that. So imagine what that graph would look like. All right, hopefully you sketched it in your mind or on the paper. You can control what percent you inspect. So you can put that on the x-axis. And total cost in dollars you would put on the y-axis. If you inspect everything, you're going to spend a lot on inspections, but you're going to have very few returns from unhappy customers. So you'll have a lot of spending on inspections. If you inspect almost nothing, you will spend very little on inspections, but you will have lots of angry customers who are upset with that the product you sent them didn't work. So you'll have a lot of cost for returns and lost business because people are upset with you and go to your competitor. So you probably have something like that, and we're looking to find the minimum total cost there. So we're trying to find that x value. So these are fairly straightforward situations, at least from a calculus point of view. Actually estimating what those curves are can be difficult. But a more complicated situation doesn't happen too often in one variable, but happens a lot when you have more variables. You might have so some kind of cost there, and could be inspection percent or whatever. What if your function goes like this? So there's kind of two things you could do that are reasonably good. You would like to choose this one. So here's our first big bit of vocabulary. There's something called a local minimum, or a relative minimum. And that's something that's as good as or better than all nearby points. And then we often contrast that with a global minimum, which is also sometimes called an absolute minimum. I don't like that term because it's not involving absolute values at all, but some people will still like to call it that. And that's as good as or better than all other points. So not just nearby points, but all points for the problem altogether. So which of these points would you call local or global or relative or absolute minimum? Take a sec to think about that. So this one is a local minimum. It's better than all the points in some small neighborhood nearby it. This one is a global minimum. It's better than all the other points. And it's also a local minimum because it's better than all the points nearby. So that's our basic vocabulary, and then next we're going to talk about how we actually go about finding local and global minimums, or maximums. I guess we could say this one, is that a local or global min or max? That's local, it's better than all the nearby points, but it's not as good as this point out here, if that point's even allowed. Maybe we can't push the temperature that high on a bioreactor, or that's over 100% inspection or something. So that's local maximum, and we're not sure how far out here we can go.